All right, so well, we've been doing energy this entire unit, and so the next form of energy that we're doing is heat, or heat transfer, or also called thermal energy. We'll get to that. But heat is the transfer of energy from a warmer body to a cooler one. Since energy is moving from one source to another, there is a change in temperature. All right, so most times we want to know how much heat or heat energy is gained or lost by something, by a body, and that symbol is Q for heat. All right, and so we have a formula, and we have Q is equal to M times C times delta T. I don't have a delta, so I always do a little hashtag. And again, here's what we've got is Q is heat. And that's in joules because we're talking about energy here. M is our mass, which we know standard units always has to be in kilograms. Just started cutting the lawn now. There we go. All right. And C. Now, C is something a little bit different. It's called your specific heat capacity. And that is the ability for something to gain heat or how much heat it takes for something to warm up. Right, because some metals or some objects heat up quick, some objects do not heat up quick. And so they have different specific heat capacities. And then our delta T here is equal to your, again, delta math and science has changed. And this time it's changing temperature, not usually our T's been time, right? Well, this time it's temperature because we're dealing with heat. All right, now where the specific heat capacity, as I mentioned, is a measure of the amount of energy needed to raise the temperature of 1 kilogram of the substance by 1 degree. So that's what it's talking about. So the higher your specific heat capacity, the more energy is needed to heat that object up. All right, so let's try a few questions here. I wish I had one of these still. 500-liter hot tub. And for those of you who don't know, I'm assuming you probably don't, that 1 liter is actually equal to 1 kilogram, is at 20 degrees Celsius. The specific heat capacity of the water is 4,180. How much heat is required to raise the hot tub's temperature to 44 degrees? All right, so again, I'm going to write down some of the information I have. A 500-liter hot tub. Well, if 500 liters is 1 kilogram, then our mass is 500 kilograms of water we're raising it at. It's at 20 degrees now. We'll get to that. The specific heat capacity of the water is 4,180. So that is what's called our C value, our specific heat capacity. We're not going to worry about the units because there's a bunch of them. It's crazy. All right. We are looking at how much heat is required to raise the temperature to 44 degrees. And so our delta T is we're looking at the change in the temperature. It ends at 44. It starts at 20. So if I'm looking at the change, I'm going to take 44 minus 20. And so if I do a little math here, that would mean the temperature's gone up 24 degrees. And what we're looking for is how much heat do we need? All right, so again, I'm going to write down my formula that I have where we have Q is equal to M times C times delta T. All right, now I'm just substituting in my values here. Again, the mass, 500 liters, same as 500 kilograms. Specific heat capacity, 4,180. All right, and that change in temperature is going up 24 degrees. And so if I just multiply those three values, I'm going to get a big number, aren't I? Let's see here. Whoa, I get 50,160,000 joules of energy it would take to heat up that hot tub. So that's 20 degrees is like room temperature, and 44 degrees Celsius is like, well, we're at like my hot tub, like 105, somewhere in there. A lot of energy, though. That's probably why I had to get rid of it. All right. Let's see here. Next up, how many grams of iron? Heat capacity is 450. See how it was much lower than the water? The water was like at 4,000. This is 450. And so iron's easier to heat up, is what that's saying. But anyways, how many grams, okay, of iron, heat capacity is 450, would be required, would require, I should say, get rid of that D, 11,000 joules of heat to raise its temperature from 22 to 40. All right, so again, let's get rid of this D. There we go, bad English on me. All right, so how many grams? So we're again looking for mass. So, all right, so heat capacity, again, that is our C value, which is 450. All right, we know how much heat's going to be raising the temperature, and that is actually just 11,000 joules of heat. All right, and we're going to raise its temperature from 22 to 40. So again, I can find the delta T. Its final is 40, and I subtract where it started. And so the temperature would be up, going up 18 degrees. All right, so again, I'm going to write down my formula here. Q equals M times C times delta T. We know the Q this time, right? 11,000. All right, the mass, we don't know. The C there is 450. And the delta T I found out was 18. All right, so I need to simplify this. Well, what I can do, 11,000 is changing, but I can take 450 times 18. And again, when I'm multiplying, it's in any order. So I usually put the number in front of the letter. So I got 450 times 18 is 8,100. All right, and then I'm going to divide here by both sides by 8,100 to get mass by itself. All right, so those 8,100s or 8,100s divide each other out, and so I got the mass down here. All right, when I take 11,000 and I divide it by 8,100, I get 1.36 kilograms. But again, this question, because it's in standard units, everything we do is in standard units here, but this question is saying how many grams? And so to get from kilograms to grams, because there is 1,000 of them, 1,000 grams in a kilogram, we're going to multiply by 1,000. And so in terms of our grams, the mass is going to be, let's see here, 1,360 grams of iron. There we go. So we just found the mass. All right, let's see here. What else we got? Aluminum. These are all true values, by the way. I didn't make these up. Has a specific heat capacity of 902. What change? Oh, I heard a little ding there. So check it out.
Oh, it was
yeah. Kayla, I didn't know you're supposed to be in the meeting. I messed up the shape of the day, so sorry about that. Again, I'm taping the video here, so taping the lesson. Yeah, go ahead.
What does M stand for again? Like in this?
Mass.
Mass, okay.
Yeah, mass. All right, so let's see here. Example 3. Aluminum has a specific heat capacity of 902. What change in temperature would occur if 34,000 joules of heat were applied to 200 grams of aluminum? All right, so again, I'm going to write out my values here. So the first sentence, it tells me the C value is 902. All right, what change in temperature? That's my delta T I'm looking for here. Just putting everything down in order. Oops. All right, what occur if 34,000 joules of heat were applied? Well, there's our amount of energy, 34,000 joules. Mass, it says 200 grams of aluminum. And that is no good to us. We need it in our standard units, and as we just looked at the last example, there is 1,000 joules or 1,000 grams in a kilogram. So I'm going to divide that 200 by 1,000. I get 0.2 kilograms. All right, here's our formula once again. Q, our heat, is equal to mass times the specific heat capacity times delta T, which is our change in temperature. All right, so we know the heat this time again, 34,000 We know the mass in our standard units. And C, we know it too. Okay, 902. And now we're looking for the delta T, the change in temperature. All right, so again, just working through the math here, 34,000 on the left. 0.2 times 902. 0.2 times 902. Again, going to two decimal places. I have 180.4 times delta T. Separate that up a little bit. All right, and let's see here. Then, well, to get delta T by itself, I'm just going to divide here both sides by 180.4. Whoa, 180.4. And so those divide each other out. And so my delta T is going to be whatever 34,000 divided by 180.4 is. And I end up getting, whoa, that aluminum is now going to go up 188.47 degrees. The metal heats up really quick. There we go. Any questions so far? All right. Let's see, what do we got? No, we got a couple more here. Example 4, if 64.5 joules of energy are transferred to 5 grams of a material that increases its temperature by 100 degrees Celsius, what is the specific heat capacity of the material? Okay, so again, let's check it out. If 64.5 joules of energy, so that is our Q again. That's how much energy, heat we're putting in this substance. Transferred to 5 grams of material. So again, grams, right? That's not going to help us out. We need to be in our standard unit. So I got to take 5 and divide it by 1,000 to get into kilograms. And I get 0.005 kilograms. Got to be in our standard units here. And that increases its temperature by 100 degrees. Well, that's our delta T here. Flat 100. All right, and this time we are looking for the specific heat capacity. And this is actually a way that some people could tell what type of material you have by heating it up and see how fast it heats up. Is one of the ways they do it, or how much energy it takes to heat it up. Then they can identify the material. All right, so then we have, let's see here, Q equals MC times delta T. All right, once again, we know our Q, 64.5 joules. Our mass, really small this time out, 0.005 kilograms. We don't know our C, but we do know our delta T, which is 100. All right, now simplifying things. Left side of my equation is not going to change. And again, when you do multiplying, it doesn't matter which order you do them in. And so I'm going to take this 0.005 and I'm going to times it by 100. And when I do that, I get 0.5. And then I'd multiply by the C. All right, and last step, I'm going to divide both sides by that 0.5. All right, so those divide each other out. And it turns out my C value will be whatever 64.5 divided by 0.5 is. And the C value is 129. And so if you were able to measure how much energy you put into a piece of material and see the temperature difference, you can get the specific heat capacity of material. And in this case, a C value of 129, this is, believe it or not, this is actually gold in real life. That's a specific heat capacity of gold. All right, so if you had that material, you'd be thinking you'd be rich. You're going to make some money. Only it's 5 grams, but still going to be worth something, that's for sure. All right, let's see what else we got here. One more. A 50-gram piece of iron with a heat capacity of 450. With an initial temperature of 547 degrees, loses 10,600 joules of heat. what is the final temperature of the iron? Okay, this one's a little tougher. All right, so to start off, is that we have our mass there, which again is in grams, which again we're going to have to convert to kilograms. And again, there's 1,000 grams in a kilogram, so I'm going to divide by 1,000 there. This time I get 0.05 kilograms. All right, this iron has a specific heat capacity of 450. Now the Q value, it loses 10,600. Whoops, Q value. Going to lose that much energy. All right, so we're going to be able to figure out the change in temperature here. All right, and that's what's left. We're going to have to find the change in temperature before we actually find out the final temperature. All right, because this formula we have doesn't have the final temperature in it. All right, but we do know it starts off with 547. All right, but we know it loses heat. So we're going to have to subtract a number here. All right, so let's get that number. All right, so we have our formula again. Q is equal to M times C times delta T. We have 10,600 joules are lost. Our mass here is 0.05. Specific heat capacity, we got that. That's 450. And we're going to find the change in temperature here. All right, so again, just simplifying things. I'm going to take that 0.05 and I'm going to multiply it by 450. And I end up with 22.5 times delta T. All right, so going to divide both sides here by 22.5. Whoops, 22.5. All right, so those divide each other out. All right, then I have my delta T. Whoops, I can draw it now. Delta T, a little triangle. We have 10,600 divided by 22.5, and I end up with, 471.11 degrees. Now that's the change. We're not done yet here, right? Because this is losing heat. All right, so if I want to find my final temperature, TF, I guess TF, there like that. We started off with 547 degrees, this temperature was, but now we know it's going to change by 471.11, and in this case, it is losing it. So I'm going to subtract space. All right, and so our final temperature of this material, this piece of iron, is now going to cool down to 75.89 degrees. I can't even draw that on here. Well, maybe I can. Degrees Celsius. There we go. And there we go. So that is, again, another form of energy that we're looking at, which most of us have experience with, especially in the last week where the weather's been nice. So it's kind of nice to have some heat energy. All right, so, I'm going to go back to your question there. In example one, yeah, it's 4,180. Let me see in the homework there. Let me check that out. Sorry, I'm not seeing where you're seeing that. Where are you seeing the 4.1? The 4.18. It's probably in scientific notation is what you're looking at.